Okay, the normal distribution is probably the most important chapter there is in S2. Virtually everything we're going to do from here on in will come back to this chapter. The normal distribution, does anybody know anything at all about it at the moment? It's a formal distribution. On the board when you came in it said it was a continuous random variable. Sometimes it's known as the bell curve, purely because of its shape. Its shape is that sort of shape. It's used for lots of natural phenomena, lots of natural measurements. It may be that if you went outside and stripped all the leaves off a tree over there and measured their lengths, you would have a few short leaves, a few long leaves, and far more leaves of a sort of average size length. So what we would have here in that case may be something looking like this. You'd have length of leaf along the bottom, you'd have, say, frequency up the side, you'd have something that looked like that. Short leaves, not very many. Long leaves, not very many. But as you got towards the average length of leaf, you find more leaves of that length. It's a continuous random variable. We did continuous random variables before the summer. What can you remember about continuous random variables? Billy should be able to remember at least one thing. But what can we remember about continuous random variables?
Oh, if you pick one variable, the probability is 0.
Yeah, probability of any specific value is 0. That's right, that's the one that I knew you would remember. Okay, anybody else remember anything about continuous random variables?
Use integration to find
We use integration to find probabilities, okay. That's when you have the formula, which sometimes I think I called the PDF, probability density function. Here's the PDF of the normal distribution. F of x equals 1 over sigma 2 pi square rooted. Then over here there's a big E and minus a half x minus mu over sigma all squared. How do you fancy integrating that?
King is B.
Okay, you don't have to. Okay, so that's a 1 over sigma times by root of 2 pi. Then that's an E, and then this is all a power on the E.
What's the sigma? Is that just a variable?
I haven't told you what the sigma is yet. Okay.
I'm thinking that sigma is in like power summing up. See?
No. This thing here, okay, it's a lowercase sigma. It's that. Yes, it is the standard deviation, as somebody said. Yeah.
How do you work this out? Is this like really random?
Somebody clever did it. Somebody cleverer than any of us, probably. And to be honest, because it's so scary and nasty to look at, we actually never use it.
So what's the variables in the bracket on the power?
Here, x minus mu over sigma all squared.
Is that a half?
That's a half there. Yep. Yep. Okay. But that is so nasty, we don't use it. Okay, we don't use it. So nasty we don't use it. But that's what it is. I wanted to show it to you because there are bits of that we will pick up later on. But if you look at this so far, important things in it are clearly this, and that is the lowercase sigma. As somebody said earlier what that stood for, that stands for the standard deviation. I'm actually going to put in of the population. So if I was talking about leaves on the tree, that sigma would be the standard deviation of all the leaves on the tree. How you would find that out? You'd have to measure every single leaf on the tree. Okay? We'll get around that problem later on.
Can we do that in the lesson?
No, we won't do that in the lesson because it would take the rest of the year aspect, okay? And in lots of questions, you will see at A-level, a tree has leaf, and it will say the standard deviation is 2.3, and which you think, who knew that, who worked it out. The answer I'm going to give, probably the same as Greg may remember last year. I think I just said the great God of statistics just knows that. You don't worry about where it comes from. It's totally unrealistic in life. You don't know the standard deviation of every single leaf on the tree, but we're not going to worry about that now. Okay? You've got this mu over here. Okay? Mu, lowercase mu. What is that then?
Coefficient of friction.
Not in this case. Not in this case, the coefficient of friction. Okay? Mean, yeah, okay, it's the mean of the population. Okay. Going back to continuous random variables from last year, and given the fact I've drawn a curve up here, can anybody remember anything that may link in with that? Continuous random variables, certain features of them, curves.
The area always equals 1.
Area underneath equals 1, and that's true here as well. So here, say we've got this length of leaf again, and we've got this graph here. The area under the curve will still equal 1. That's because it's a PDF. So that is still the case. The area under the curve will still equal 1. I have a slight issue here, in that whilst that's obviously not the best drawing that could be done, I've deliberately not joined up the end of the curve with the x-axis here or here. That tail there, in theory, goes on forever and never touches the x-axis. What sort of thing is that called? An asymptote. Yes, thank you. It's an asymptote, which occasionally I can spell.
How would that...
You would have really need to go to negative values of length or something.
Yes, but as they got closer and closer to the x-axis, because this is the probability here of those lengths, the probability gets infinitesimally small as the length of the leaf gets infinitesimally
Possibly
big.
get a length less than 0.
Yes, that is true. It's another thing that we just don't worry about in this, okay? In real, can I just address that first of all? In real life, there are other, in real life, it sounds terrible, this isn't real life this year, this is A-level maths. In real life, even in A-level maths, there are more complicated distributions which you can actually have chopping off points. You can say, actually, nothing will go beyond here. You haven't got to worry about it. This is it. Whilst it's still S2 and not S1, it's still an introduction to probability theory, and we just don't worry about those things for the time being. Billy?
I was about to say that, like, how do you get... Because with discrete data, obviously, you're going to have more than certain size.
So, yeah, I mean, here, you're quite right. That tail will go on over here, and we could end up in negative numbers. We just don't worry about that, because the probabilities would be so small. Okay, we just don't care. Okay? Right, 2 more drawings. If you can just draw one that looks quite tall and one that looks quite wide. The area underneath is still supposed to be the same, it's supposed to be 1. This one here is one that has a small standard deviation, so a small value of sigma. This one here would have a large standard deviation, because remember, standard deviation is a measure of spread. And at that point I'll stop this video and start it again in another bit. Okay, the next bit, the Billy special, as it is known. If we have these leaves here, and we may know that the average length of leaf, and this curve is symmetric, the curve is beautifully symmetric. Say we knew the average length of leaf was 8 centimetres, and here we have the frequency, or the probability is what we're really dealing with here, probability. The probability that a leaf length is 8 centimetres is, Billy?
0.
0.
It pains me to say that.
It pains you to say it, but it's 0. Yeah, remember, Billy is our expert. Probability of it taking any specific value is 0. You will never find a leaf that is exactly 8 centimetres long.
I'm guaranteed to get that wrong in the exam.
You could always, in theory, measure it more and more accurately and find out actually it's 8.00000000001 or something like
So
that.
Billy going out and doing this experiment to find one now.
Billy wants to do that. It's up to Billy.
You're doing like the probability of picking a number, and obviously the probability of picking the number 8 is possible.
Not if you're choosing from all continuous numbers.
Yeah, but it is though. It's definitely possible because number 8 is like bang on.
Yeah, I would have thought it is.
part of the set of continuous numbers.
Yeah, because it is.
But it's one continuous number out of an infinite number of continuous numbers. So the probability would be 1 over infinity, which is 0. So, if you wanted to know the probability that the length of the leaf is 8 centimetres to the nearest centimetre, what are we really talking about there?
Between 7.5 and 8.5.
Yes, we're talking about 7.5 to 8.5 for the length of the leaf. That's the less than sign. Should I put extra equals bits on there?
It doesn't matter.
It doesn't matter. That's again a Billy special. It doesn't matter because either ends have no probability attached to them. Okay. So if you wanted to know, the length of a leaf is 8 to the nearest centimetre, then you'd do it between 7.5 and 8.5. Right, now, when I did this...
normal distribution.
Sorry?
So that's still the normal distribution.
Still the normal distribution,
It's
yeah.
the same as the...
It's continuous random variable? It's a continuous random variable, yeah. It's one of many...
Oh, so the normal distribution is part of this.
It is a continuous random variable, yeah. Okay? Right, what we're going to do now is we are going to look for at an example, I suppose. I got here that we are going to pretend that we know about all the boys in year 13. Greg, we didn't have any girls in our group last year, did we?
No.
Which is apologies. This is why. Okay, it says boys in year 13. That we know that their mean, and I'm assuming we are talking the heights, is 175 centimetres, and their standard deviation is 6 centimetres. And those are their heights. And I actually think from looking at my notes last year, we actually measured everybody in the group because in the maths room I had a tape measure going on the wall. Do you remember that, Greg?
Yeah. Things can use in practical maths lessons.
No.
Like go out and do math.
You would have...
I'm not asking myself that, so
So, but in the moment...
Mr. Powell got things we could throw at walls.
Did he? No, I know the second motion one where he went to the courts and ran out.
What we're going to do here is we are just going to pretend we have this knowledge. And I will just occasionally use the sort of tongue-in-cheek phrase, the God of statistics has told us that this is true. In real life, you wouldn't know unless you went round and measured the height of every boy in year 13. So if we're sort of doing a question and in an exam they tell us that sort of information, we need to get in the habit of writing stuff down correctly, formally, in notation. So we start off with a capital letter to define our variable. This should ring bells to what we did in the binomial distribution and the Poisson distribution. Capital letter to define our variable, and here x will be the height of a year 13 boy in centimetres. And the question may say assume that it follows a normal distribution. Well, people's heights generally do if they're taken from a population. You would probably get some short people in year 13, some tall people in year 13. Shouldn't be pointing at people now being heightist at the back. Okay? And then average sized people, more of those in the middle. So the way we write this down is this. X follows that tilde, that little curvy thing we've used before. The normal distribution, we just use an n. When we did the binomial distribution, what sort of came after the b for binomial?
Elements of...
In the brackets with an n and a p, okay? When the Poisson, we had a PO, then a bracket, and what went in the lambda, that's right. For the normal distribution, what goes in is the mean and the variance, not the standard deviation. So, the first number is the mean, the second number is the variance. Which is a bit annoying, really.
Why did you put in the variance when the formula is just this?
It's it's a very good question. We actually use the standard deviation far more than we do the variance, but the person who invented the normal distribution's formal notation, every textbook anywhere always puts the variance in there. So rather than write it down as 36, which means later on you've actually got square root 36 to work out what the standard deviation is, it's common just to write standard deviation squared in there. Okay? So the key thing, your first red box rule effectively, is you write down x is normal and then it's mu sigma squared that goes in there. Now, what we would have to do in a minute, but let's try and work out a question in a minute. Let's try and find the height of... I've probably got one here. Let's have a look. We measured Alex. That would be Alex Jones, wouldn't it? Alex Jones we measured last year being 195 centimetres. Since there's no tape measure over here, we'll just go with this again. So we had Alex with 195 centimetres. And what we wanted to do was find the probability that any year 13 boy we chose at random was smaller than Alex. That's the sort of question we were coming at. So the question might be, find the probability a randomly chosen year 13 boy is shorter than Alex. So, if we just think about what we've got, we have got a graph, and it's always useful to do a sketch. A normal curve does not have to be beautifully accurate, it's just a sketch. What do we know about it? We know the mean. This graph is always symmetric. The mean, unsurprisingly, is in the middle. So that's 175. Alex's height was over here, 195. So to find the probability that a randomly chosen year 13 boy is shorter than Alex, we want this area here, which is the integral between minus infinity, because this never actually touches the axis, and 195 of that horrible thing we saw earlier. And we don't do it, because it's too horrible to even contemplate doing it. And at that point I'm going to stop this and start another video. Okay, we've just said that integration is too horrible to even contemplate doing. I asked the class, well, how do you think you do it? Someone said, stick it in your calculator, and I said, if you've got a graphics calculator, yes, you can. Then I asked, thinking back to what else we've done so far in S2, what have we done? And people said, we've used tables. In your tables, if you find page 19, you see this, the normal distribution function. Now on here, it doesn't give you a choice of mu, and it doesn't give you a choice of sigma. There aren't pages and pages of tables for different values of mu and different values of sigma. For the Poisson, there were tables for different values of lambda. They took up pages in the book. But here for the normal, you've just got one page of tables. And what we do is we convert every problem to have the same mean and the same standard deviation, and then we work on that converted problem. So what we had here in this example was our question said x was normally distributed 175 6 squared. We now do a conversion process which changes that to a normal distribution with a mean of, and if you look at the table in front of you, you'll probably work it out, with a mean of 0 and a standard deviation doesn't actually say on that page. Greg? It's another very basic number.
1.
1. Yes. Okay. So we convert every problem from its original mu and sigma to be a new problem with a mean of 0 and a standard deviation of 1. And instead of being x or whatever we called it up here, this is called z.
How'd you get mean of 0?
Just the region on the side of an axis as well.
That would be correct, yes. So this one up here, this one up here would have been centred on 175.
Yeah.
This one down here will be centred on 0. That was an x scale. This is a z scale. It will be centred on 0, that's correct. What do we do to x to make it into z? That is the key thing. There's a hint in that very horrible formula we wrote down at the beginning, in the thing that's a power on the e. What was...
You meant that equals.
Oh, well, can't we shift it down by the...
You shift it down.
That way x minus the standard deviation. No.
It's not minus the standard deviation.
Minus the mean.
Minus the mean, yeah. If I took 175 off every value there, that curve would just slide left, and then its mirror line wouldn't be above 175, but would be above 0. So z, first thing we do from our x is we take away the mean value. That purely slides everything down the number line. So now it's not centred above 175, but that has fixed it to be centred above 0. The next bit, the standard deviation bit, this fixes its shape to be consistently wide or narrow, if that makes sense. But it fixes it. Then we now divide that sigma. And that is your next red box rule. Z is x minus mu over sigma.
Is that the capital X?
In this case it is, but normally after this case actually it will be, we'll pretty much always use a lowercase. Okay. But z is a continuous random variable in its own right, so I could use an uppercase one there.
What's happened?
I took a bit of paper off.
No, I didn't really follow through on that.
Okay. We do this magic thing here.
Yeah.
Whatever our original distribution was,
Yeah.
from every x value I subtract the mean, and when I've done that I divide by the standard deviation, and that changes it from that distribution to this distribution. And this distribution here is the one whose probabilities are here. So once you've done that, you can use this, and that z there is basically the value you get when you do this transformation here. So if we keep going with this, find the probability somebody is smaller than Alex, I'm just going to write it all down again. Well, not write it all down again, just write down the basics here again. We had this distribution, and we were asked to find the probability that somebody was smaller than Alex. That's our distribution, that's our question. What we do is we change that value there, which is a specific value of x, so that's a little x value. We need to change that question into a probability that z is less than some specific z value. So that's an uppercase z, that's a lowercase z. So we need to work out what this z value is using this transformation that we've got here. Well, in this case, z will be the x value we had for Alex's height, take away the mean height of all the boys in year 13, divided by the standard deviation of all the boys in year 13.
So 1.5 Z.
Oh,
Sorry?
1.5 Z. What were you putting in 1.5? Is that an X?
Here,
No, you put an arrow.
There.
What's that?
That's a little x. That's a specific value that big X took there. So if you work this out, what is Z? As a number, as a decimal number, it's actually more helpful. I'm sure you can convert it into decimal.
Yeah.
It's 10 over 3.
10 over 3. So that means, and I'm going to draw two diagrams now just to really sort of emphasise this point. I'm going to draw two diagrams, one under another. One is an X diagram, one is a Z diagram. Originally, I was dealing with a mean of 175 and I wanted to know about 195 and I wanted to know that area there. I converted this into a Z diagram with a mean of 0 and actually I'm now interested in, and if these were drawn properly that would sort of be underneath it, I'm interested in 10 over 3 which is 3.33. So I'm now interested in, on this new curve, this area here, and those areas are the same. And now what I do is I look in my tables and I find 3.33 in my tables, except 3.33 is actually off the scale. Yes.
Well, you just round 3.33 or 3.33 recurring?
The tables only go to so many decimal places, as we'll see. Okay, actually I could go to 3 decimal places there. Okay. Right. If you look at the tables, the Z values go down the side here. Either Alex was so tall, or I just completely underestimated the average height of the year 13 boys and forgot to correct that this year. That actually 3.3 is off the scale down here. Okay? So, can we just pretend that the great god of statistics has made his only ever mistake, and the average height of boys in year 13 is not 175 centimetres? Can we make it 185, yes. Okay. So, let's just pretend a minute just to make this work. I ought to have made a note of this, so this didn't work last year. Okay? So, what we're doing now is we're changing mu. You can't really do this normally. Okay? Because the great god of statistics got it wrong. And we will say actually that mu was 185. Let's remember not to use that example next year. What calculation will I do then to get Z? Now I'm still dealing with Alex. Alex is still 195 centimetres tall. Was Alex really 195 centimetres tall? Maybe he was. So, what calculation will I do for Z? I will do the person's height, take away the mean, divided by the standard deviation. What does that come out to be this time? Yes, that's exactly right. What is that? 1.6 recurring, yeah. So if we do it to 1.667, if you do it 3 decimal places, that's accurate enough. I'm just going to stop here because I'm running out of time in this video. Yeah, do it to 3 decimal places, that's fine. Now what we need to do is find Z being 1.667 in our tables. So we come to our tables, here's Z, here's 1.6. Now we go along, if I use a bit of paper as a ruler.
Well, you're not, because you're not doing it for 1.7.
Well, we'll do it at 3 decimal places. Okay? There's 1.6. There's 1.66. You happy with that? Okay? So there's 1.6 on the left. Here's 1.66. If I want 1.67, I look over here under my 7 column and I've got to add 7 onto that. Now I don't actually add up integer 7.
Wait, so
Instead of
if you want 1.667.
yeah, if I want 1.6 is 0.9452. 1.66 is 0.9515. 1.667 is add 7 onto 9915. You get 9522. Okay? So if I write that down a minute, if we're using the tables, we said that a z value of 1.6 we could read off really easily. That was 0.9452. 1.66 we needed to go across our tables, across that row until we're under the 6, and then it said 0.9515. Then when I added the extra decimal place, that's 7, what it said over on the right was I had to add on 7. So I did 9515 plus 7 is 9522, so I get 0.9522. We can do another one of those in a minute. But that would mean if we chose a random boy from year 13, the probability they were shorter than Alex is 95%. Yes, 0.9522 probability.
If it was finding they were bigger, would it be 1 minus that?
Yes, it would. Yeah. If it was finding they were bigger, it would be 1 minus that. If it was finding they were exactly the same height as Alex, 0. Yeah. Billy didn't even say the answer that time. Very disappointed. Okay. 0. Yes, that's right. Okay.
Is that if you, for the opposite, so essentially you pick it out, you just take it, but then you take it away?
Yes. If you wanted to do a greater than, these tables here are less than tables, and it's really important you know that. The clue is they shaded in to the left of the z value. So these tables here always give you the probability of being less than, or less than or equal to, because they're the same. If you've got to do greater than, or greater than or equal to, you just do 1 minus your answer.
People stop at 2.9, or would they go on as just the simple stop?
They effectively stop, because if you look over here, 2.99 is already taking you to 0.9986.
Does this work if you're looking for the probability of less than something that's like way to the extreme sides of the movement, or would it work?
Well, it would just be that they would have to print these tables to more than 4 decimal places. And in real life, if something's that unlikely, it doesn't crop up very often, so they're not in here. If you did it on a calculator, then in a minute, what I want you to do is find out how you get that number out of the calculator. You could probably put in that one that we had that wasn't never going to work for Alex, 3.33, and it would probably give you 0.999999, something like that. Yeah.
Why is it if you put in just 0, it comes out exactly 0.5?
Because of the symmetry of the curve. To go back to the drawing I had here, this is a transformed Z curve. It's always symmetric around the mean. We fiddled it, the Z thing, so it was a mean of 0. So the probability left of 0 is half the curve, 0.5. That's where that comes from. Right, now your challenge, because I can never remember how to do this and calculators change each year, I don't know whether Greg will help us out with this, but if you find somewhere on your calculator something to do with a normal probability, possibly a cumulative normal, you will need to put into your calculator a mu value, a sigma value, an x value, and if you can get an answer out of 0.9522, you have found all the right buttons to press. Okay, I'm going to pause the video at that point. In a minute, when someone's done it. Oh, Ben, can you do it now? What? Can you show us on here then? Okay. If you show it on here, we'll record this as well, this bit.
Or is it on here?
Okay. Zoom in with the T if you want to.
I think you're right.
Okay. So, can you all listen?
Right, so just go into stats, and then distribution with F5 on the green ones. I'm not sure if it's the same on the blue ones. And null, and then cumulative enters.
NPD, MCD.
NCD is the cumulative one. NPD is just sort of that point. Then you put in the lower, which is 0 in this case. Upper is 195 because it's the value we want.
Can we? I don't know if we can zoom in a bit. See
Yeah,
actually your
it's not
screen a
quite
bit
there, is
better. Hang on.
It's a bit dark. There we go. Kind of.
This standard deviation is 6.
Yeah, and then you put your
Mine didn't say that. Mine gives me like a. You need a sigma and a mu.
oh, what? Sigma and
I've got eldest.
yours probably does differently. Is yours a blue one?
Mine's a sigma and a mu.
Yeah, yours is a better calculator.
Would make more sense
And then
to me, I think, actually. But basically, if you can get that on your calculator, you probably found the right thing.
so yeah, that's
You want to take yours up
It's the
here?
same, it's just a bit numerous. So.
yeah, yours is a bit nearer calculator. So
Can you do yours as well? Does anybody know what calculator Chelsea's got? Because she'll be watching this and trying to do it. Okay, so you can do that on there, okay? Okay, so just talk through what you're doing again on here.
So,
Like from scratch. So you know exactly where you've gone from the opening screen.
I'll go back to the home menu. There, so you go to stat, distribution, normal, and then cumulative. And then the lower is 0, because you can't be smaller than 0. The upper is the height of Alex. So it's finding the probability of anything between the upper and the lower. And then that's standard deviation, which was 6. And the average, the mean we said was 185. And execute. Should give you that.
Okay.
I've just got a few extra figures in.
Thank you. I'm just going to stop the recording at that point. Right, Sinead, what should we measure about the girls? Yeah, but we're going to talk about the girls. What should we measure?
I don't know.
How much they can lift. Okay, right. How much they can lift. Okay, great. What do you think the mean is? We just got to invent this for time. What? Right. The great god of statistics is telling us that they can lift
10 kilos.
10 kilos. With a standard deviation of 2 kilos. Okay? Right, now we have observed from the girl that we have in front of us, called Sinead, that Sinead can lift 13.5 kilograms. Now, what we want to do is find the probability that a girl can actually lift that. So our question is going to be, find the probability a girl can lift more than or equal to 13.5 kilograms. So, sorry you couldn't see that as I was writing that. If I go off the board, please tell me, because I haven't got a monitor here to see what I'm doing. So, okay, yes. Find the probability the girl is basically as strong or stronger than Sinead. Okay. First thing we need to do, we need to define our variable. X is what you normally use, and that will be the mass a girl can lift. We are going to assume that X is normally distributed. And what do I write down in the bracket? Which are
10 and 2.
and the mistake Billy's made? No.
Square.
Yes, remember that is sigma squared, even though we don't use it. Okay. So we have that. What are we trying to do? What's our question in this notation? What is our question? Yeah. Okay. That's the question. So, first thing we need to do is, that question is not user-friendly. What we need to do, and this is a red box rule, is you change a greater than to 1 minus less than, which is exactly what somebody said earlier on.
You like move monitor up a little bit. Down. More, please. Thank you.
Okay? So yeah, we change a greater than into a 1 minus less than. So actually, we are going to change the question into, well, what we want is 1 minus the probability that x is less than 13.5, because that's the same thing. If I do a drawing, and it is worth doing these drawings, we have a mean of 10. Sinead could lift 13.5. We wanted that probability over there. Thank you, Rob. We want this probability over here. We have said, because our tables do the other way round, what we are going to do is 1 minus the red area, if you can make out that that is red. Okay? So, what do I need to work out? What calculation do I need to do first? Because I cannot deal with these x's with 10s and 2s and things. Yeah, I need to work out my z value, which is always x minus mu over sigma. The x is the value 13.5. Mu is the mean, which was 10. Nicely chosen to make a nice easy sum earlier on. Sigma is 2. What does that come out to be? 1.75. So what we need to do now is go to our tables and find z is 1.75. First of all, you can find 1.7 really easily. 1.7 is listed down the side. When you find z is 1.7, can anybody tell me what the probability is? 0.9.
599.
Okay, you're one step ahead of me actually, yeah. For 1.7, and we wouldn't normally bother writing this down, but just so you can really see what's going on. 0.7 is that, but what we want is 1.75. So if you know you found the right row, go over until you are under the 5, and then we get 0.9599, if I've read the right number. Is that our answer? The probability that a girl can lift as much as Sinead or more than that?
1 minus.
Yeah, I need to do the 1 minus. So set up here, I need to do a 1 minus. So my answer will be 1 minus 0.9599, which is,
0.04.
or as a percentage, we can say about 4%. There's a 4% chance of finding a girl as strong as Sinead.
No, they're as strong as 0. They're stronger, isn't it?
Well, there's a probability they're as strong or stronger, yes. Yes, as strong or strong, yeah. Okay, you think that technically I was incorrect, correct, yes. As strong or stronger. Okay? In an exam, if I was writing that question out, we'll start off like this, but this bit here was absolutely fine. Okay, saying what mu and sigma is, that's absolutely fine, or sigma squared. We wanted to know the probability that x was greater than 13.5. That's absolutely fine. What we then do is turn that into a 1 minus a less than. That's absolutely fine. The new bit I want to show you is this. When you are doing the probability x is less than something, we do this. Phi basically means find the probability that z is less than. And then in here, you just do your x minus mu over sigma. So that's how you write that down. So at that stage, that is 1 minus, that's that 1 minus, and phi x minus mu over sigma. That is the z value, but actually in the exams, we don't usually bother writing down, you actually using the letter z. We just go straight to here. So in the exam, we would get 1 minus phi of 1.75. Phi of 1.75 means look 1.75 up in the tables, just like we did earlier. We said that was 0.9599, and we get our answer.
Would you get marked down using that?
No, you wouldn't. Okay, but how we will be doing it from now, how the book will be doing it, how mark schemes will probably be doing it is, you just use this phi here. Phi means find the probability that z is less than that, and that's just normally how we will lay it out. And that's where we're stopping for now.